My name is Michael Weber, and I'm a faculty member at the University of Texas at Austin. I'm in the mechanical engineering department, and I teach a lot of classes, do research on topics like energy and water. And I also help run the Energy Institute there and the Clean Energy Incubator, which helps foster startups in this space. And we're now launching the Water Technology Incubator also at the University of Texas. So I'm in the space of education, research, policy, and commercialization, all on those topics of energy and water. We call it the Energy-Water Nexus, or the Water Energy Nexus, or the interconnections of energy and water. And the short story is that we use a lot of energy for water, and we use a lot of water for energy. And this is both a good news and a bad news story. So I'll talk about how we use them for each other. We use water for energy for things like driving turbines and making steam for power plants and growing biofuels. We use energy for water for like heating, treating, moving, chilling water to get to the place we want it. And the numbers at the national scale are quite large. About half our water withdrawals every day are just to cool power plants. And about 13% of all our energy consumption is just for the water system, to heat, treat, move, chill, pressurize, clean water. So we're using a lot of energy for water, a lot of water for energy. Now the bad news is it introduces vulnerabilities or constraints, where you have a problem in one becomes a problem in the other. If you have a water shortage, it becomes an energy shortage. If you have an energy shortage, it becomes a water shortage. So that's bad news. The good news is we have solutions that can solve two problems at once, in particular like conservation, or smarter meters and better data and advanced services and systems, where you get water conservation achieves energy conservation, whether you meant that or not, and energy conservation achieves water conservation. And it's usually cheaper to save one by saving the other, which is sort of the irony. We use more water in our light bulbs and our electrical appliances in our house than in our taps and shower heads, which is surprising, because we use that water to cool the power plants that make the electricity. And we use more energy in our water and our taps and shower heads than in the light bulbs, which is really surprising as well, to heat all that water. And so if you save water at your taps and shower heads, you're saving energy. And if you save energy, like the light bulbs, you're saving water. And if we have better information, better data, better analytics, better controls of the systems with metering, sensors, ubiquitous sensing, that kind of thing, we can find a pathway to solutions. And that's the good news of that interconnection. I think the big trend that I'm looking for and I expect to happen is moving from interconnected energy water systems to integrated energy water systems. And I'll explain what I mean. With the today's system, the conventional system, energy and water are interconnected. Energy needs water, water needs energy, and then if you have a problem one, it becomes a problem the other. It's ad hoc or accidental. We have connected them without a lot of thoughtful purpose in doing so, and it introduces problems. Well, I'd like to move from that accidental, vulnerable system to the intentionally designed, integrated system where we use water and energy together for a very specific purpose of getting cross-cutting gains. So I can think of a variety of ways we could do that. We could use the wastewater from power plants to irrigate biofuels, or we could use renewables like wind and solar to desalinate brackish groundwater to get fresh water. You put those together and you solve two problems at once. So let's take wind and solar. Their challenge is they're variable. They come up and down with the weather. And that is a challenge for the grid to manage the variability of the supply of power along with the variability of demand for power. Well, what if you coupled that with a water treatment or a desalination plant where you could vary that water treatment up and down to match the supply? So all of a sudden, you solve the problem of the desalination plant needs so much energy, but you can provide it with low carbon, clean solar and wind energy. So you solve the water sector's problems and you create a supply of fresh water in the process. And that water treatment plant solves the energy problems, which is the variability because it takes up the variable supply.
Right.
So if we go to intentional, thoughtful, integrated engineering design, we get cross-cutting benefits. In our current system with accidental, ad hoc, interconnected systems, we get cross-cutting vulnerabilities. So I think that leap in thinking is where we need to go. A lot of our legacy system is operating blind, I would say, using 100-year-old meters that don't have much information, or zero meters. There's some place in California where there were no meters, and so you didn't have any information at all, or the information was faulty, or the meters are buried underground, that kind of thing. So we don't have data, and it turns out it's hard to manage something if you can't really see what's going on. And so getting access to better data, higher fidelity data, data updated more frequently, or data that's more precise and accurate, and managed in a way that's easy to keep track of, that will help us get to a better solution. Now, data isn't enough. I've got a fascination with Dr. Pepper. I really like Dr. Pepper. And on the cans, it says right there how bad it is for me. I've got all sorts of data how bad it is for me. Turns out that's not enough, I still drink it. And so we need more than just the data, we need price signals or other cultural forces. But if you raise the price of corn syrup and you had ads everywhere that says, don't drink that, you'll get fat, then probably I would change my behavior. Overall, I think that the technologies, there are all sorts of technologies, that a lot of them offer a lot of value, and we need to have a whole suite of options. Metering, sensing, data are a part of it, but then we'll need demand reduction devices. We'll need more efficient valves and flow controllers and things like that. But those will be worthless if you don't have the data as a part of it. So we have to have it all integrated as a suite of options, and then we can achieve real gains.